Okay, so today we're going to cover sections 11.3 through 11.5. 11.3 is about stable and unstable nuclei. So nuclear decay and the nuclear radiation which it produces is the result of unstable nuclei. And so an unstable nucleus is one which is just barely holding together. We can think of some unstable chemical compounds like nitroglycerin that is ready to break apart and release a lot of energy in that process. Well, nuclei themselves are held together with these powerful, strong nuclear forces, and some of them are very stable, and some of them are unstable and ready to break apart. These unstable nuclei are what lead to nuclear decay. And there's a pattern in which nuclei are stable versus unstable. So this is figure 11.2. This is sometimes called the belt of stability. And what you see here are a bunch of isotopes that have been discovered. And on the x-axis is the number of protons in the nucleus of that isotope. On the y-axis is the number of neutrons in the nucleus of that isotope. And so we can find a few familiar elements on here. You can find, if you look at 12 protons and work your way upward, then you'll see that there's carbon 12 and carbon 13 and carbon 14 that are, where are we? 10. Carbon only has 6 protons. That makes so much more sense. Okay, perfect. So if you look at 6 and you work your way up there, you can see that 6 protons and 6 neutrons is blue, that's carbon 12. 6 protons and 7 neutrons is blue, that's carbon 13. And then there's a bunch of red ones on either side, and in particular carbon 14 would be the red block on top of those two blue ones that is the most common radioactive isotope of carbon, although you can see that there are a whole host of carbon nuclei that can be generated in a laboratory setting, and most of them are extremely unstable and would decay very rapidly. Anyway, so you can see that you need to have like the perfect ratio of protons to neutrons. For small elements, that tends to be about 1 to 1, but if we were to extend this graphic out further, we would see that the larger elements require more and more neutrons. And that's why you'll see for something like carbon, the mass number is about double the atomic number. But for elements beyond that, like let's look at one like uranium, right? Uranium's atomic number is 92, that's 92 protons. But the mass numbers of its isotopes are like 230s to 240s, so quite a lot more neutrons than protons. So we're going to look at a couple of different types of decay processes today, and I just want to point out that some of those decay processes are going to increase the ratio of protons to neutrons. They'll correspond to shifting rightward on this chart. Those are the decay processes that will happen for isotopes that are above the blue line here. And this will make sense in a minute, but that would be beta decay, for example. And then there are some decay processes that will tend to decrease the ratio of protons to neutrons. And those would be things like electron capture or positron emission. And they'll be processes that occur for isotopes that lie below that blue line. So that is the belt of stability. So you may recall we talked about different types of radiation. There were alpha particles, which are just a helium nucleus traveling at high velocities. There were beta particles, which are just an electron traveling at very high velocities. and then there were gamma rays. Those are only the most common types of radioactive decay byproducts. And we'll see there's at least one more, which we call a positron, which you could represent with a beta and a plus down there, and you'll see why. But anyway, so these are the things that are emitted, but let's talk about the actual chemical reactions that lead to decay through these processes. So the first one would be alpha emission. And an element which undergoes alpha emission is uranium 238. And uranium is the 92nd element. So we're going to write that there as our starting reactant. A total mass of 238 and 92 protons. And that is going to decay, and it's going to produce an alpha particle. And you may recall an alpha particle has a mass of 4, and it has 2 protons in it. And to balance nuclear reactions, we just basically need to balance the mass and the charge. So the alpha particle is not the only thing. There's going to be the daughter nucleotide to uranium-238. In other words, what uranium turns into after it loses this little bitty alpha particle. And so let's look at the total mass. It was 238. 4 were lost to the alpha particle, so we'll have 234 as the mass of our new nucleus. And then uranium had 92 protons, but it lost 2 of them to the alpha particle, so we'll have 90. Now we go look at the periodic table. What's element 90? It looks like it is thorium. So we've got a sort of a figure that shows alpha decay. This is figure 11.3. So you see the uranium-238 on the left, and then it releases the alpha particle, which is really just a helium nucleus, and we're left with thorium-234. And so we were able to determine that thorium just by comparing to what was lost from the uranium and consulting a periodic table. So do you want to try one more? Yes, you do. This isn't Dora the Explorer. You can't talk back to me. Okay. 208, 84, polonium. And I should point out that uranium-238 is a naturally occurring isotope of uranium. You can go to a mine and you can dig up some uranium and you're going to find uranium-238. In fact, it'll be probably, I think the majority component of uranium would be the 238 isotope. But other elements don't occur naturally, and that's because they decay so rapidly that if they were formed early in the formation of our solar system, which was, what, 8 billion years ago or so, then they'll have long since decayed away. So polonium is one of those. Most of the larger elements beyond uranium are going to be ones that you don't find in nature. So where do you get polonium from? It's generated artificially through particle colliders or through nuclear reactions which we drive in nuclear piles or nuclear reactors. And so polonium is one of those. Anyway, polonium will undergo alpha decay. So we know that one of the products will be a 4,2 alpha particle. What will be the mass? 208 minus 4 is 204. And then 84 minus 2 is 82. And I don't know what the 82nd element is, so let's see if we can find it together. Here's my periodic table. And that's 112, 80, 81, Looks like 82 is lead. Oh, you can't see the tooltips, but when I hover my cursor over lead, it shows that that is element 82. So we'll put PB. There we go. We've balanced the alpha decay of polonium. Now let's look at beta decay. So in beta decay, essentially you'll have a neutron converted into a proton and the beta particle, which is an electron. So you'll notice that this little mini equation balances out, right? 1 plus 0 is 1, 1 plus negative 1 is 0, so that all balances out. But this process will be happening to one neutron that is in the context of some larger nucleus. And so let's look at iodine 131. Iodine 131 will decay via beta emission. And iodine is the 53rd element. And so we'll do the same thing. I told you it decays via beta decay, so you know it's going to have 0, negative 1, beta. And we'll want to balance everything out. So it started at 131. The beta particle is 0, so we'll end at 131. And then the 53 is going to equal 54 plus the negative 1. You gain a proton, right? So this number will increment by 1, and that is xenon. Xenon is the daughter nucleotide or the beta decay product for iodine 131 decaying. Let's look at another one. 55 chromium. Chromium is the 24th element, and it undergoes beta decay. So here's our beta particle, and we'll have a mass still of 55, but instead of the 24th element, it will be the 25th. What's right above chromium? It looks like manganese. So that would be Mn. That is beta decay. Now, gamma emission is kind of a special case here because most nuclear decay processes will emit a gamma ray. They'll emit a photon of light carrying high energy, but excuse me. But we'll usually not write it. It's kind of just assumed because we're more interested in the alpha particles and the beta particles. They're the reason why nuclear numbers are changing, why elements are transmuting from uranium to thorium, for example. But there are some reactions which will actually just release gamma ray. And one of them, I actually don't have the whole balanced reaction, so I need to look up hafnium here. Give me a second. That'll be 178, 72. Okay, so 178, 72, hafnium, and I'll just write star there. And what that means is that this is a sample of hafnium that has been previously exposed to nuclear radiation, and it has absorbed some energy, putting its nucleus into an excited state. And over time, hafnium will decay, and it will decay to emit a gamma ray, and balancing this one is easy as can be because the gamma ray has no mass and no charge. So here the hafnium has returned to its ground state. This is a lot like phosphorescence. glow-in-the-dark things like watch hands or balls or whatever. Glow-in-the-dark things will absorb energy when exposed to light and then slowly release that energy over the course of time afterward. That's why they glow in the dark. Well, hafnium glows in the dark too. It glows in gamma rays instead of glowing in like a pale green light. So here's an example of gamma radiation being emitted in the absence of other sorts of nuclear decay byproducts. Okay. So let's do now positron emission. So the positron is actually the antimatter equivalent of the electron. And antimatter is weird stuff, and I'm not a physicist, so I won't offend them by trying to explain with my limited understanding of what antimatter is and how it was discovered and why we are certain that it's a real thing. But a positron, being an antimatter electron, actually carries a positive charge because charges are reversed in antimatter. And so in positron emission, it's kind of like the opposite of beta decay. You'll have a proton converted into a 1, 0 neutron plus 0, 1 positron, right? So that's a positive one. And you'll see this little mini equation balances. Let's see it at work. The most famous positron emission nucleus is potassium-40. Potassium-40 occurs naturally, and geologists have been able to use the positron emission of potassium to date the date of formation of different rocks that contain potassium. Because potassium will decay into, we'll put the positron there. The mass will be the same, 40, but now this will be reduced by 1. So 18 plus 1 is 19. And what's the 18th element? It's argon. Okay, so that is positron emission. And then one last mode of decay, and that is called electron capture. And this is where the electron and a proton are going to combine to form a neutron. And so this is usually a core electron that is already a part of the element, and not like an electron coming from the outside. Electron capture. Mercury will undergo electron capture decay. So we have Hg 197 80, and we'll write the electron here in order to help us balance things. But again, it's actually one of Mercury's own electrons. We've just kind of singled it out. This is the electron that's going to get captured, and it will form 197 79. And that is gold. And so you'll notice the transformation that electron capture causes is equivalent to positron emission. That is, that you have the same mass number, but your atomic number is reduced by 1. The way we tell the difference is by detecting the emission of a positron. If a positron is not detected, then it must have decayed via electron capture. And those are the modes of nuclear decay. And table 11.2 really kind of summarizes this, the sorts of changes that take place The change in the atomic number and the change in the mass number are really the only two numbers that you need to identify what isotope is going to be the product of your nuclear reaction.